뭘 하지 않냐? 미소 금융에 집중을.
So we make a recreation time about secondary dusting system. Just for you, right? Just for you. What we see commonly is like this, yeah? This is Danieli design, yeah? And I say this is a stupid design. Why? Imagine you open the roof and you charge a basket. And then you get a huge panache here. Even flames everywhere. Yeah? This design imposed to suck everything which is coming. And you have peaks up to 140 megawatt in 20 seconds.
So many seconds.
Yeah. So you need a huge suction capacity. The intelligent design is something like that, even with some deviation plates, and you put pipes here. And with openings on top, and vent on the side. This is designed as a vacuum cleaner, but vacuum cleaner, the dust is on the floor, it doesn't move, so it doesn't escape. If, in this case, if you don't have enough suction capacity, what happens is that here, the panache is coming here, and if it doesn't suck immediately, it's getting cold and it's fall down again. Because here there is no speed enough. Because when you close the roof, there is no more heat sources to push the gas up. And there is no way for this dust in the lower layer to get out of in the duct. It's falling down again. You can go everywhere in Danieli steel plants. You have permanently people with brooms to clean the floor. Yeah, everywhere. And if you don't care about the side wing, this is from the top. Here you have the furnace. Yeah? And sometimes, I mean, mainly you have doors here. Doors. Yeah? And you have side wings. So, and you have the canopy hood here. So, the panache is going even in this case, in this direction. And this dust has no way to get down. Yeah, because the panache is so big that it cannot be absorbed immediately. In this case here, this canopy is acting as a buffer. You store the off gas. Of course, you suck here when it's coming, then you accumulate the gas in this area. You have recirculation, yeah, and you suck where is the colder part. And then when the dust is coming down, it's getting sucked again by the duct. Yeah? So you get a better efficiency. To settle you an example, this is a 100-ton furnace, 110 even, 100-ton furnace, with a tap-to-tap of 45 minutes, having 2.8 million cubic meter per hour. People roaming on the floor. In this case, twin shell, this is just a 100-ton furnace having 6.8 meter in diameter. This is twin shell, 150 tons, 7 meter in diameter plus the distance between the two shells. This is something like 18 meters. With this concept, 1.6 million cubic meters, our capacity of the secondary, and no people roaming on the floor. Yeah? Of course, this case has been big enough, yeah, in order to receive all the panache produced by the charging. And you have to design this box able to receive the complete panache and to keep this panache for about, let's say, you allow you to empty in 15 seconds. Yeah.
You mean the right side case, the tunnels, all the area in the tunnels, the minus pressure is not.
No, here you have overpressure.
Overpressure.
Oh yeah, if you have small hole, you will see fuel escaping. Because this is the hot temperature. Yeah. I made it in 3D if you want to understand.
Okay, we understand fully.
Yeah. And on the side, you have the pipes. Going in, close at the end, with the openings on the side.
Okay, I understand.
Or even, sometimes we see also these designs. Yeah, and openings here. But the openings is more efficient because you can control better the distribution.
I know.
Yeah?
I understand.
But all the time on the bottom of the box, never on top. All the time on the bottom. And you have to be sure that on the side, these walls is coming down to the frame level as low as possible. Yeah.
I know.
Yeah.
Yeah. I see.
Because I've seen so many dialing plants, the crane level is here. Yeah? Crane level is here and there is no wall. So the gas can go everywhere.
Okay.
So Danieli, never mind Danieli.
I get it.
Response time.
만족했습니까?
근데 그날로 말안 했는데.
레크레이션 타입입니다.
레크레이션 타입인데.
Hey, do you think that in 3 months you will
토픽에
remember?
집중할 시간인데 우리가 지금
sorry?
Do you think that in 3 months you will remember the meaning of this sketch?
I
파일 하나
saw
지금
this
디스플레이
sketch
Yeah.
in other places
그 집은
in
내가
America.
좀 받아서 분석을
So I know this is
Shall we start?
the case.
Oh, you are so excited by the electricity, yeah?
Huh?
You are so excited by the electricity or what?
Existing?
By this completed. Oh, somebody destroyed my formula.
No. No touch. No
Oh,
touch.
I was afraid, huh?
No touch.
So we keep this formula for tomorrow morning. Yeah, let's have a look on this small calculation help for the temperature. Because how to know the off-gas temperature? Eh?
And today we would like to finish this files. of gas system.
Of gas system. Yeah. So that's why I'm coming to the of gas temperature. In fact, I made a thermal balance. I know the post-combustion energy. Post-combustion energy is this amount of CO2. Yeah. All right. Because what you have to know is that when you blow oxygen in the bath, you just create CO. You don't create CO2. Yeah. So my hypothesis is that all the CO2 what I have here has combusted in the furnace shell. No energy is going into the bath. So then I have the radiation from the start. Yeah, maybe I'll finish. So the 6.55 is the energy to convert CO into CO2 at 1600 degrees. Yeah. And this is the difference between what I consider, I mean, here I consider 30% of the post-combustion useful for the bath heating up. And this F88 is what is really happened at the exit of the elbow. Yeah? This F58, 88. Okay? So this is the post-combustion energy. Then you have the radiation of the bath. So this is the bath surface at this temperature in Kelvin.
You assume that molten steel temperature was 1640, yeah?
1640 is the bath temperature, I mean the surface of the slag.
Surface,
Yeah. Because the temperature of the slag is all the time higher than the temperature of the bath.
slag is more higher.
Yeah. And because the arc is heating
of
the.
course,
Yeah. So in Kelvin, and this is high 4. So this is the radiation from the bath itself, minus, you see B26 plus B27. This is the surface of the roof and the surface of the panels. Here, B26 and 27. And I consider that we have a slag layer radiating at 800 degrees C.
Slag?
Slag layer.
slag layer.
I mean, the panels are coated with slag.
앞에 판넬 쪽에 slag 붙은 거.
Okay?
그것도 퍼펙트다.
So this is the emissivity coefficient. And this is to convert into megawatts. Yeah?
Yes.
Because the emissivity is in kilocalorie or something like strange unit. Yeah.
Yes. What is 0.85?
Something I guess like the 0.9 from this morning. What is the 0.85? I don't remember, honestly, I don't remember. Well, anyway, so this is the total energy we have available, and so the water is taking a part.
Yes.
So in fact, I just have this energy remaining, I just is already a lot, yeah, for the off gas under the roof. So I calculate the temperature of the off gas under the roof. So K57. This is the energy. Yeah, to convert into kilowatts, and I guess this is the off gas amount, F91, 91, and this is the CO2. I just consider CO2. Ah, yes, excuse me. Because in this case, I have a big difference between the heat capacity of the CO2, nitrogen, and the rest. So I consider them independently. Yeah. So this is the flow rate of CO2 times the Cp of CO2 plus the flow rate of 92. This is the oxygen times the capacity of oxygen and nitrogen. You see, oxygen and nitrogen are very close to each other, but the CO2 is much higher. Yeah. So that's why I made this difference. So I put all this energy into the off gas, and there is no calculation. No. So this is the binary formula to have the air ingress, and this is the dilution after the gap. But basically I would consider this temperature. I should have something in a macro maybe. I will have a look and I will tell you later. Because I don't understand why I don't have a formula here. Because between this stage and this stage, usually I should take into consideration the fact that I'm continuing the post-combustion in case it's not finished, and minus the thermal losses in the elbow. Yeah. And then afterward the dilution. So this gives only an indication for me to put this temperature. So what I am able to calculate is the off-gas temperature during refining, because conditions are stable. During melting, conditions are unstable. So it's a matter to take a temperature between, let's say, 100 degrees and this temperature, which characterize the average of the off-gas temperature. This is not scientific, yeah? This is empiric. So during the cigarette break, your people were mentioning the additional requirement regarding off-gas calculation. Yeah? So you will have what is available today, and you will see what you need additionally, and you will tell me, and I will implement.
외국인도 가져왔어요.
지금 이건 평균값이거든요. 그 셋을 따라갖고 많이 나오는 경우가 있잖아요. 가스를 많이 넣거나 산소를 많이 넣거나. 근데 그런 데 대한 대안이 없냐고 물어봤죠. 지금은 평균값이라 지금 모든 값들이 나오는 게. 프로세스가 그 밖에서 기체를 넣어주는 양에 상관없이 시간대에 대한 평균값이거든요.
근데 어차피 앞에 산소 양이나 뭐 에어 양 넣는 게 있잖아. 그거 조절하면 뒤에 바뀌는 거잖아.
그 값을 바꾸면 당연히 바뀌는데 그래도 그거는 그 시간대 평균값이지 중간에 이렇게 가면서 맥스 값에 반응이 일어났더니 그 값은 아니라 이거지. 직진 나갈 때 제 맥스 값을 고려해야 되니까 그래서 그건 문제죠.
집중률 맥스 값을 그러면 전액 틀리지. 그렇게 따지려면 원료에 따라서 발생하는 걸 다 고려줘야 되거든요. 그래서 기름기
방금 뭐라고 물어봤습니까? 이제?
아니 뭐 두루두루 포커스 관련해서 다른 것도
네.
그랬다고 하길래 내가 뭘 요구했나 싶었어요.
그걸 요구했어요. So what's the point? What did you ask just before? You said.
You were attending the cigarette break on,
Yes,
on
yes.
the roof, and you were mentioning that okay, this is average
Yes, yes.
flow rate, but sometimes you have peaks, so we would like as well to know this value of the peaks, because to dimension the dusting system, this is not enough.
Yes. 아 지금 그러면 저걸
And I was mentioning that I have already another one. Which is dedicated more for the shaft furnace, but I have to adapt this calculation sheet for the conventional, where as well you have all the dimensions here, yeah, of the furnace pressure and furnace temperature, but this is the shaft feature. Oxygen injection is precise here. And then calculation of air ingress, so here you can forget, and you have here what is happening during scrap caving. You have additional 0.08% per minute. No, excuse me, this is this value. This is the actual decarburization rate, plus here you have in kilogram per square meter and per hour, what's coming from the scrap caving. Yeah. So this can be included for scrap caving here. You see, this is the case of scrap caving. So you have oxygen injection produced, this is the oxygen, the CO produced, and the gas coming from the burners, creating CO2, supposedly, and H2O. So you have this amount of gas generated by this injection.
Yes.
But you see that I don't have additional gas here for the caving.
This is not what I was doing.
I should have some caving here. Okay, no. It was obvious. Yes, this is coming from the injection. And this 13 additional CO production is coming from this reaction. You understand?
Decarburization.
No, this decarburization is the different thing. E82. Ah, this is this one. And F82. And F82. This is this reaction.
Yeah, what's the
Because there were two people involved in this field. One who was talking about percent per minute, and the other one in kilograms per hour, per square meter and per hour. So that's why I put this calculation. But this is the same value.
yes?
This is 280 kilograms per square meter an hour, converted into percentage per minute.
You know, that is just the decarbonization rate.
No, this is the additional decarburization rate occurring during the boiling. Yeah? That's why I inject oxygen. So I get 10,000 cubic meter CO.
Yeah.
Additionally, I have this reaction. That means in total I have 23,000 cubic meter CO. Alright?
Yeah. This is not what I was telling you. Just what I was telling you before. Just I want to know the off-gas amounts according to the process, right? According to time intervals.
Yes, so you have it during melting. You see, during melting, I inject 5,000, get 10,000 CO from the injection, burners, and this is the small, because painting, you have painting on the scrap, you have plastics and stuff which are burned by the air. So this is the small amount coming from this burning stuff, and this is the burners. So you have this gas composition, yeah, still with CO, where you have to burn the CO, yeah. So you get this amount of gas here, and to burn the CO you need additional air. Yeah. You see, you need 13,000 cubic meter air. Okay?
Then what's the difference between this one and the one you showed us before?
You mean this one here?
Yes.
Oh, here I consider only an average. You see, this is the total amount of carbon I have to burn. Here I consider dynamic situations. I inject this at this time, so I get this amount of air, of gas. Of course, it's not the same furnace. Yeah? Here is a 120-ton furnace with 5,000 cubic meter injection of oxygen.
Is this considered when the is this considered as the maximum of gas amount?
Here you have it. This is during scrap caving. This is the maximum of gas you get. This is the unburned gas, for which you need additional air. The air is here, 70,000 cubic meter air, and you get at the end 85,000 cubic meter. For this application.
If you see the analysis, it was less than 500, 50,000 cubic meter, right, per hour. If we see another sheet.
Yeah,
Another
just put
expression,
here, let's say normal condition. No scrap caving. Yeah? scrap kevin.
What's the scrap cabin?
스크랩 넣을 때 그래요.
아,
그때 맥시멈으로 나와요.
Boiling.
아니
과장님이 그
보일링.
맥시멈 옵개수를 얘기를 하니까
This gives you the maximum capacity of the dedusting, primary dedusting.
이게 보일링 할 때, 트레이팅 할 때 되는 거야.
그러니까 그거 하면 볼링하지.
아 그래서 그때
아, 그때 경우가 이거라고.
맥시멈으로 나올 때가 스크랩 케이밍 할 때라고.
스컬키링.
This is worst condition.
worst condition.
Yeah.
맥시멈 옵개수를 얘기를 하시니까 이 상황을 가지고 이렇게.
So this is something you want to see over. Okay?
될 텐데.
아니, 그렇다고 지금 이 사람이 이걸 우리 준다는 얘기는 아니거든요.
당연하지, 그렇지. 근데 굳이 맥스 전기로 조업을 할 때 보면 대부분 이제 그 저기 필름 난다는 게 이제 처음 스타팅 할 텐데 그러면서 저기서 이제 가장 많이 날 때도 있고 안 날 때도 있거든. 사람들은 이제 왜 양질의 그 고철을 쓰냐면 그런 게 적다고. 근데 이제 우리 같은 뭐저 터닝제라든지 이런 걸 쓰게 되거나 아니면 페인트가 묻어있는 우리 그 캠이라든지 영양 이런 거 있잖아. 그런 걸 쓰게 되는데 거기서 오일이 타거나 그런 불이 많이 나고 거기서 이제 페인트라든지 이런 이물질들을 쓰면 연기가 많이 나온다고. 그때 이제 그거는 잡기가 어렵다고. 그래서 이제 그 후드를 두고 지붕에서 잡는 거지.
어차피 저건 지붕으로 나가는 고려할 필요가 없는 건데, 그러면.
아니 지금 배가스 나중에 집중 전체를 할 때는 집중기에서 빨아들이는 것과 이제 후드에서 뭔가 합쳐서 온도도 다운시키고 그거랑 믹스를 시켜야 된다. 그거는 전체의 집중 컨셉을 잡는 개념에서 들어가는 거니까.
그러니까. 근데 어차피 제약이 저렇게밖에 안 된다면 온도도 많이 안 갖고 있고 저 위로 올라가고 하면 찬 공기 많이 잡하니까 고려 안 해도 되는 양이지 저렇게 되면.
아니다, 그것도 고려해. 그게 이제 또 왜냐면 그거랑 여기서 전기로서 나가는 거랑 온도 자체를 또 믹스시키는 어느 정도 다운시키는 된다고.
But
그런 게 고려되는 거예요.
now, I mean, you may have two different philosophy. Yeah?
네.
The old one without canopy hood. And without canopy hood, the purpose was to be able to suck on a primary this kind of peak. Yeah? With regulation, damper, and so on. With canopy hood, now the tendency is to say, okay, I have a scrap cave-in, but I don't care. When the primary suction system is not able to suck, it will go to the hood.
Yes.
And flame will escape from the furnace and that's it.
그러니까 지금
So in this case, you have to consider the average flow rate plus a certain safety margin because you don't have, let's say, under pressure under the roof, but over pressure in case of scrap cave-in. So you will have more suction. So you need to keep certain safety margin of 20%, for example. And the rest will go to the canopy hood. Huh? So, in this case, you don't need this kind of calculation.
요것만 같으면 필요 어떻게
아니 그러니까 아니 그게 아니고 이제 핵심을 좀 잘 봐야 되는 게 뭐냐면 여기 있는 이 사람은 전체를 다 보는 엔지니어가 아니라고 전기로에서 있잖아 기본적으로 들고 나가는 에너지하고 매트리얼만 본다고 나머지는 이제 우리까지 이제 토탈을 하는 라인 미터들이 이제 그걸 하는 거라고. 그러니까 이제 그때 발생하는 양이 그러면 예를 들어서 선행제 같은 거 기름 많다 그걸 끌고 갈 거냐 말 거냐 위로 뽑아내는 거냐 그럼 전체 집중이 높게 얘기하는 거야. 그게 여기서는 맥시멈까지 필요 없고 단지 그것만 필요한 거라.
이것도 포함시키자고요?
돈 필요 이거 줄 달라면 줄 거야. 그러니까 이것도 같이.
So you can give these files to us.
아까 요거 하면은 포함시킨다고 했잖아.
그거는 그게 문제될 게 아니거든. 저는.
So also, can we have these files?
This is useless. Useless. Because this is exactly the same calculation from the other side.
really?
but with, let's say, differentiation of, let's say, phases with the burners and phases with the stuff. Because it was designed in this case to get all, because this is designed for shaft furnace, yeah? And the purpose, of course, is not to let the energy going out of the furnace, but to get all the energy in the shaft to make preheating. Yeah. So it's useless for you. But you have to tell me what you need exactly additionally compared to this calculation. Yeah? So make up your mind and just tell me. Okay?
Just let me have it.
Huh?
Let me have it.
Yeah.
Okay.
No problem.
Thank you, my teacher.
No,
My teacher.
no problem. So we have seen almost everything on this calculation sheet, except the carbon calculation. So, back on this. So on this sheet, for example, I will put $1 additionally. Yeah. So you see, the cojet is fixed by the process, and is given here. You see the burner mode, the lancing mode, low fire and high fire. So in this sheet I have all the flow rates, and I calculate 3 minutes burner time, and then I can switch to the high fire. You see cojet gas, low fire, then high fire, 1.5 megawatt, and then switch to lance mode 10 minutes later. And then come the second basket and start again the same procedure. I have no third basket. And then comes the refining phase.
If we choose the 3 basket, the calculate the 3 charging P3 is calculated automatically.
Yeah. Yeah, but here I just have 2 baskets here, you see. If I decrease I have too much density. Uh-huh. 7.8 is rather large. Now I have 3 baskets. Yeah. So, of course, the third basket is coming automatically. Yeah. So, I design here the cojet burner time. And then this is the door length.
Door is flat door.
The door length is not used for the first basket, neither for the second. For the third basket, 50%, and refining 100%. Yeah. So automatically I calculate the oxygen amount, and I will see on the diagram here megawatts. and the cojet time, and the lens here. Yeah. So this is the gas from the cojet, and this is the oxygen of the cojets, and this is the lens here, the blue line. And of course, these volumes will be integrated in the oxygen calculation here. And if I have one power off for the temperature measurement, and can vary the time where I take the sample. You see the lines. This is a gimmick. Okay?
Yes.
So, all the process, all the informations of the diagrams is coming from this process sheet here. And DRI, in case I have DRI, the logic is as following. This is the DRI profile. Yeah? First, I start 2 minutes with low flow rate, then 3 minutes with, let's say, medium flow rate, then I go to the maximum flow rate. Of course, the diagram has been changed because due to this this beamer, everything has been changed. But this line is at the end of power on, so I stop the DRI 1 minute before power on, and 2 minutes before power on, I decrease these steps here. And you have it automatically calculated in this part of the sheet.
오늘 이 정도 여기까지 하면 어떨까?
좋습니다.
5시.
네.
그리고 일단 저녁 보고 할 거 있으면 하고, 일단은 내 생각에는 이제 우리가 지금 제일 중요한 거는 일단 전기로 노내하고 그것을 뽑아내는 거, 그게 제일 중요한 거 아니겠는지 보면. 그러니까 진짜 그거를 이 사람이 가진 걸 많이 보고 그 달라야 돼. 이거 끝이 아니단 말이야, 그지? 응? 전기로 이거로 끝이냐는 거 보면 이것만 해가지고는 어렵잖아. 우리 지금 바꾸자면 다 받았나? 다 했나? 배터리 밸런스 있고, 트랜스포머 일단 들어가 있고, 프로세스 다이어그램, 오퍼 스페시피케이션, 프로세스 디스크립션 이런 거 남았네.
그거는 소프트웨어 포함 안 된다고 그러죠.
그래, 그건 아니고, 이게 다큐멘트잖아, 이거. 그리고 이거를 내가 봐서는 예제를 3개 정도 포함해서 스크랩만 했을 때, DRI 스크랩 했을 때, 그지? 그 다음에 예열 설비가 있을 때, 이렇게 3가지를 받아야 된다고. 그리고 비교를 해볼 수 있는 거야. 소프트웨어 받고, 이게 아웃풋 된 거랑 이거 보고 좀 비교해서 다 쓸 수 있게끔 해야 된다. 이거만 하면 여기서 다 받았다가 밑에는 끝이잖아. 이제 LF 남았고, 그지?
아니, 아주 아까 C 컨텐츠인가? 그거는 내일 한다고 했어.
How about finish the today?
You want to go to the carbon calculation then, yeah?
Yeah, tomorrow.
Tomorrow is better.
Because I think we also need some meeting 30 minutes.
Yeah.
And 지금 예약 다 해놨지?
네.
We already booked some restaurant at wheelchair. And 6시 반에 바로 가서 하지 뭐, 그지?
네.
No problem. I go back to the hotel and you pick me up there.
Yeah.
Huh?
And first you come back hotel on foot, and we will pick you up 6:10.
Okay.
그 대장금 6시 반 하고. Unfortunately, I have to go to my boss's funeral. Yeah, I will come back early morning next day, and I will participate in 9 a.m. Next day.
All right.
So enjoy the dinner, and maybe Saturday or Friday one more time we have a dinner party, and then I will obviously enjoy with you.
Okay.
Okay.
My best thought to your boss, huh?
Okay. In Korea, have to kill the